Very much, Susan. Thank you all for being here this afternoon. I'm very happy that Jay Brophy, agreed to give this presentation. He really needs no introduction to this audience, but I'd like to just take a few minutes to say why I invited him to give this particular presentation. So Jay, some of you may not know, is one of those rare people who completed a master's degree in chemical engineering before he went on to study medicine and specialize in cardiology. So he's someone who has a very keen analytic mind. And of course, he must know something about cardiology. I can't say, but I do know that he has an appreciation for statistical methods and statistical programming and keeps abreast of these things as they are relevant to epidemiology. Even at this stage in his career where he could easily delegate that kind of task to somebody else. And so during the last year of organizing the seminar series, I've noticed that, biostatistics seminar speakers can come from a varied background, some more theoretical, some more applied. And this topic on DAGs is something that many of you requested wanting to hear about. And it's something actually I myself know precious little about. And I thought that an applied take on the subject would be far more relevant and illuminating than something which is extremely theoretical. And I'm sure that Jay will be able to share with us his knowledge and add to our knowledge over here. Jay, apart from what I already mentioned, is a teacher of the intermediate epidemiology course at EBOH, where he covers advanced epidemiological methods and among them DAGs. So thank you, Jay.
Thank you, Nandini. There we go. Let's just share the screen, hopefully. All right. Can you just give me a thumbs up if you can see the screen all right?
Yes, it looks good.
All right. Thank you. Yeah, well, thank you very much, Nandini, for inviting me. And actually explaining why you asked me, because I had some trouble kind of initially figuring out why you were asking me to speak about DAGs. And I call this the view of a clinical. This is actually code for people to sort of say, hey, don't expect us to get too theoretical. So that was just a little bit of hidden latent code as to what's going on. So obviously I have no conflicts of interest with this talk, or actually with any other talk I ever give. So what are the objects? Kind of to understand and operationalize this sort of directed acyclic graphs, or DAGs, and maybe try and appreciate in a very concrete fashion some of the insights, or the additional insights into confounding and selection bias in particular that can be provided by DAGs. And then we'll go through some clinical or published examples of DAGs, and hopefully try to convince you of their importance as we sort of try to move along this road to causal inference. So let's just start with some background. And this is sort of, kind of comparing what we get compared to what we want. And if we look at the most talked about articles, this is from JAMA Internal Medicine, but you could take any journal, it's the association of this with that, the association of that, etc. The top 7 articles, 5 of them, look at this, have an association of a couple of variables. But I mean, really, we're not that interested in associations other than just one association, and that's the causal association. Excuse me, in other words, what's this treatment T or exposure E, cause outcome Y? Now, there are obviously other reasons we can have these associations, including reverse causality, confounding, selection bias, excuse me, and random fluctuations. But we're really mostly interested in this causality question. And how does the conventional statistical paradigm deal with this? And what's the comparison with regards to DAGs? And so Fisher sort of said that the object of statistical methods is the reduction of data, finding some sort of parsimonious mathematical description of the distribution of the observed variables. But while that's very good for description, it really says nothing about the data generating process and can't answer causal questions. DAGs, on the other hand, also known as causal diagrams, do try to characterize these causal structures and I think help in drawing logical conclusions. And they help understanding these various biases that can arise. So let's look at an example of a 2x2 table where we have a study with 350 people exposed to a drug and 350 controls. And there's the data in the green table. And at the end of the day here, our question is, does this drug work? And this is I'm not going to say a trick, but we look at this data and it's a bit confusing. Because if we look at the combined data, we have 78% of people who recover with using the drug, and 83% who recover if they don't use the drug. So that's sort of looks like maybe the drug doesn't work. But if you look down at the subgroups, in men, 93% recovered, more than the 87 who didn't take the drug. And similarly, in women had an increased 73% versus 69% among those who took drugs. So, you know, in the question of does this drug work, I think we would answer yes, it works. Because if it works in both men and women, it surely makes no sense to say it doesn't work if your gender is unknown. So that's, you know, this is an example of Simpson's paradox, right? Now, but the interesting question becomes, is not a general rule that more specific subgroups should always take precedence over the marginal? I mean, is this, every time we have data, should we be looking at the subgroup rather than the combined data? Well, look at a different example, but actually it has the same data, exactly the same data, just the headings have been reversed. This was drug over here and this was no drug in the other one. Now, but this experiment looks at a different drug, and the drug works by lowering blood pressure, okay? But it also has some toxic side effects. And now we have the same 2x2 table with the same data. Here it's stratified by your post-treatment blood pressure. Okay? And now let's look at the same data again. And the question is, does the drug work? Well, in the combined group, we would say, yes, it works. But if we look at the subgroups, the specific subgroups of low blood pressure, the drug apparently doesn't work. Well, it doesn't work as well as no drug. And similarly, in the stratum of high post-treatment blood pressure, the no drug recovers more than people who take the drug. But here, we actually should be believing the combined data, right? And so why is the combined data more informative here? It's the same data as we had before. And before we said we should look at the specific subgroups. And the answer to this question can only be really readily resolved by looking at DAGs. And in the first experiment, gender was really what we call a confounder, right? It was influencing the drug exposure and the outcome. Right? And so there's this sort of backdoor pathway, ACB, which is interfering with the causal pathway that we want to evaluate, namely A to B. However, in the second experiment, the stratifying parameter was low, there was post-treatment blood pressure. In other words, it was following the drug acts, you get your blood pressure, and then that goes on to whether you have an event or you don't. And stratifying here actually ends up blocking the causal pathway, right? And so the message from this is that just looking at stats, just looking at 2x2 tables, really can't allow you to sort out the causality. And the causality can only really be interpreted by the sensible inclusion of some sort of external judgment or evidence. And what DAGs are is a graphical representation of this external judgment, right? That's what the DAG is. And for someone like me who sort of is a Bayesian and likes to incorporate and bring in prior knowledge, this is really very in keeping with that. You're having to bring in some external judgment or external evidence before you can actually make sense of the data in your experiment. And I think it's worth spending a second to sort of underline the importance of trying to figure out causality, right? And so we can predict all sorts of things by putting in a ton of variables, but that doesn't necessarily mean that these variables are going to be causes, right? And so knowing a cause means being able to predict the consequences of an intervention. What happens if I do this? And similarly, it means what happens if I had done something else, right? And so this is why I think causality becomes so much more interesting than just whether there's some association which could arise for any number of non-causal reasons. So how do we put this into operation? As I said, first of all, just the raison d'etre for the DAGs is to encode in a qualitative, non-parametric manner our a priori subject matter knowledge, and consideration of the causal model may help us provide clarity in terms of how we interpret our statistics that come out of these models and the inferences we can draw. Now, since we're having to use a priori subject matter knowledge to create these DAGs, there is a corollary from about DAGs and about causal inference in general, and that assumption-free causal inference doesn't exist. So we have to be making some assumptions if we want to go down the causal inference pathway. So the top there is a DAG. We'll run through some of the terminology. We can see there are no equations, there's no betas or anything like that. So this is really, it's non-parametric. The variables, in this case, are letters. They're depicted as nodes connected by arrows. The acyclic part means that you can't circle back. In other words, the future can't predict the past. Interestingly, the strongest assumption that comes out of a DAG are the missing lines, what's not there. Okay, because that's implying that there is variable independence, right? And so this is a very strong assumption, but it's worth recalling that missing lines have a great deal of importance in DAGs. And what should be in your DAG? You must have all the nodes, anything that includes at least, it must include at least all common causes of any two variables, and all variables involved in the data generation. And this actually should be observed or unobserved data as well. And we'll see that this putting in a node for unobserved data can be very informative as to what's going on. So this will include both causal pathways and non-causal pathways, pathways that go against the flow of time or against the direction of the arrow. And the whole goal here is that from these DAGs, there are certain predictions that we can derive or testable implications of the model, and we can see if our data actually is consistent with the model or not. There's more terminology. We won't insist on this too much, but we talk about paths, and that's just a sequence of these non-intersecting edges. For example, here, X to T to C to Y. The causal pathway here is this treatment T going through C to Y. The total causal pathway is all the causal paths together. The descendants of a node or anything that comes after the node. Children would be, in this case, C would just be the child of T, etc. Ancestors are just going in the opposite direction. In very important concept in DAGs is something called a collider. And that's where you have at least two arrows coming in to a variable. In this case, X would be a collider. And we'll spend quite a bit of time as to why these colliders are important. So some other terms you might hear is a pipe. A pipe is just a little bit what we saw in the second example. A flows through C to influence B. This would mean that in this DAG, A is not independent of B, right? Because what you do to A affects C and C affects B. However, if you condition on C, then A will become independent of B, right? Here, as a confounder, confounders are common causes. It's a common cause of, and here we have it, it's affecting both the exposure and the outcome. And so consequently, A and B, again, are not independent. However, if we control for or stratify the confounder for the confounder, A and B become independent. Now, the collider is almost the opposite of the confounder. Here, the arrows are both going into the collider, and A is independent from B here. A affects C and B affects C. They're independent. However, if you stratify on C, right, or you condition on C, and you look at just one outcome, then you will create this spurious association between A and B, right? And that is initially perhaps a little hard to get your head around, but if you stop and think about it, it really does flow quite easily. And here's an example to kind of explain this effect of conditioning on a common effect. So suppose I have a coin and Nandini has a coin, and we flip our coins, and if one of them comes up heads, a bell rings, right? Now, obviously, my coin flip and Nandini's coin flip, there's no association between them, right? On the other hand, if Nandini flips a coin and I flip a coin, and you're told that the bell rings, and I tell you my coin is tails, well, suddenly there is information about Nandini's coin. It must be a head. So by conditioning on knowing that the bell rang, we have created this inverse association between the two variables. So conditioning on this common effect or collider induces a negative correlation between the two causes or risk factors. And even if you condition on a descendant of the collider, that will also lead to this spurious association, right? And we'll see why this becomes really very important and why we don't just throw everything into our multivariable regression analysis and let the computer decide for us. A final bit of DAG terminology. You'll hear about block paths. These are sometimes called deseparated for dependence separated. So as the name implies, block, they're deseparated. These paths don't transmit associations. On the other hand, deconnected pathways do transmit associations. 3 blocking criteria is if you condition on a non-collider that blocks the path. We can think back about that drug example of the post-treatment. When we conditioned on the blood pressure, post-treatment blood pressure that blocked the pathway. If you condition on a collider, that unblocks the pathway. That's just like the example on the previous slide about the two coins and the bell ringing. And if we don't condition on a collider, then that pathway is naturally blocked, right? If the variables are deseparated, that means that they will be statistically independent. And this we can verify with our data and see if our causal model holds. If they're not deseparated, then X and Y are conditionally dependent in at least one distribution along the DAG. So we can estimate causal effects, and one thing we do is we try and get a sufficient set to block the backdoor criteria. If you want, here we're looking at the association between the causal association between X and Y. We'd like to measure that, but we have this backdoor X, Z, Y, and so if we can find a set of variables to block this backdoor, then we're in a position where we can evaluate the causality between X and Y. And the criteria here would be that Z is not a descendant of X, right? Because if it's a descendant, we don't want to be stratifying or conditioning on it. And every pathway between X and Y that contains an arrow into X must be blocked by this set of variables Z. So that's known as the backdoor criteria. Unfortunately, the backdoor criteria doesn't always hold, because if you look here in the upper right, we want to measure, is there a causal association between X and Y, but we can't measure. U stands for unmeasured confounders. So we're unable to block this backdoor. Without belaboring the point, you can get into what something is known as a front door criteria. And if you have a set of variables Z, which are between them, you can use these criteria to try and determine if X and Y are causally associated. I don't want to spend a lot of time on that. It's really just a question of applying the backdoor criteria twice, but you'll have the slides, and if you read through them, they will make sense as to how this front door criteria works. So, in the simple DAGs, this is about as simple a DAG as one can come across. And so what are the assumptions that are contained in DAG, and what are the statistical implications? And how simple is this DAG, right? So you might be surprised to know that there are 16 assumptions and statistical implications from this small, simple DAG. Obviously, just looking at this, we can say, okay, well, the DAG, one thing is that X causes Y, and U causes Y, but then there are all sorts of other implications of that. X and Y are independent, right? That's another conclusion that can be drawn from this. And so you can actually list all the causal assumptions that are represented in that DAG, and this, excuse me, the statistical relationships which are implied by those causal assumptions. All right, X and Y are if X is a direct cause of Y, X and Y are statistically dependent, etc. So let's look at some additional insights. Starting with confounding. Remember the classical definition that a confounder is associated with the outcome and non-causally or causally associated with the exposure, and it's not on the causal pathway. And how do we decide if a variable is a confounder? Well, typically we've looked at statistical criteria to make this call, right? We might compare stratified to marginal effects and see if they're different, or we might have in a model looking at adjusted or unadjusted effect estimates. And often we do this with automatic variable selection. In other words, we just dump everything into our computer and we let multiple regressions sort it out. And, this is, people say, well, we're letting the data speak. In my humble opinion, if the data are talking to you, it's time to be quite concerned, right? But regression models are insufficient for a number of reasons. They offer no distinction really between causes and confounders. There's no mention about the biases, residual confounding, measurement error, missing data, or anything else in any of these models. And they actually might contain causal misinformation. And this is a so-called table 2 fallacy, which I don't have time to go into, but essentially that sort of table 2 that you get in many publications, which shows you your beta coefficient for the main variable you're after, and then every other coefficient that's in the model, and people are interpreting that as these other coefficients are causal coefficients, given that all the other variables have been controlled for, and that's actually not true at all. So all these strategies, these statistical strategies to decide on confounding may lead to bias. And so here's an example of letting our automated statistical software on the loose. So we're going to generate some data, and here we've got blood pressure, and we've generated this data according to this expression here. And you can see that the blood pressure is a function of age, and it is not a function of your drug group, right? There's no term for drug group. So this is the actual data, and the same data over here. But now we're looking at these data points, how many of them are, who's exposed and who isn't exposed. And I'm sorry, it's not very clear, but the little squares are unexposed and the circles are exposed people. And it turns out that the unexposed group seems to be systematically younger than the exposed group. But remember, the systolic blood pressure is not a function of group, right? This is we've simulated this data. We know the truth here. So what happens if we sort of say, okay, we'll pretend we don't know how we got the data, and let's create a model where systolic blood pressure is a function of age and group, throw it into our computer, and lo and behold, when we put, we control for age, and we put group in our model, the group is highly statistically significant, right? So we've created this, there's this spurious association between systolic blood pressure and exposure groups. And we know that that's not true because we generated the data with no group exposure. So, the message here is that p-values are not going to predict or pick out your correct causal model. We know the causal model here because we simulated the data, but if we just throw it into a linear regression model, it's going to tell us that systolic blood pressure depends on your drug group. Right. Another advantage of DAGs, as I've said, is kind of helping to distinguish between selection bias and confounding, which is not always trivial, right? Confounding by indication versus selection bias, what's what here. I think it is helpful to think of confounding as the effect of common causes where this is affecting exposure and the outcome or disease, as opposed to selection bias, which is conditioning on common effects, right? So confounding is a state of nature, but selection bias is an artifact of the research process. Both of these results, both of these lead to non-comparability and or lack of exchangeability between the exposed and unexposed, and have to be dealt with. Selection bias then occurs when exposure and disease outcome both affect participation in the study. Right? And typically, this is seen at the entry point in typically case control studies, but you can also have selection bias in terms of withdrawal. right? And differential losses to follow-up, which can occur in cohort studies and even in RCTs, right? You have an RCT that loses 10, 15, 20% of people to follow-up. You very likely can have a selection bias, even though this was a randomized study. So the classic terms, or classic examples of selection bias, Bergson bias, where you use hospital controls, healthy worker, volunteer basis, etc. The point is that selection bias is often quite difficult to identify and often overshadowed by other biases. But it's very present, and I think that using DAGs can really help you identify it. Here's an example, hopefully to convince you of this. Here we've said that your income, C, influences whether you go and have a medical visit or not. Similarly, if you have high blood pressure, that influences you and you're more likely to go and see a doctor. But that there is no association between income and blood pressure, right? That's what this DAG is representing. If you're interested and you like the code, this is our code which will produce that DAG for you. Okay, and so now what happens? And so let's do some simulation, right? And so we've randomly chosen 5,000 values of income and 5,000 values of blood pressure, which are are independent. And this is what the data looks like. And if we draw some sort of regression line, the slope is actually 0 because there is no association between blood pressure and income in this simulated data. But now what happens if we say we are only going to look at those people who actually had a visit to the doctor? All the dots represent everybody that was in the population, 5,000, but now we're only looking at those people who actually had a visit, right? And when we do that, those people are shown here in the teal color, and we have this inverse association, which is highly statistically significant, saying that blood pressure and income are related. However, we know, because we simulated the 5,000 points, that these are not related. They only become associated once we condition or we select on somebody having a visit, right? And if you want to produce these diagrams and the code to do it is all here. It's very straightforward. But you can see that once you start to condition on common effects, that you can create these spurious associations, right? And then that's also known as collider bias. And of course, this can also happen in terms of informative censoring. In a cohort study, or again, even in an RCT, where you have some exposure that leads to censoring. And if we have these other pathways there, once we sort of condition on people participating and not being lost, we can create these backdoors pathways. And this is why, if you see somebody who does an analysis, a complete case study, I mean, just only including individuals who have all the data or who came to all their appointments, that sort of a conditioning on that can lead to a collider bias. So if you compare confounders and colliders, you can see the contrast. One is based on common causes as opposed to common effects. Whether the pathway is open or blocked, and the effects of conditioning are opposite in these things. Where a confounder, if you condition, you're blocking the pathway. A collider, you will open the pathway. Right, and before the conditioning, with a confounder, there is bias. There isn't with a collider, but the reverse becomes true once you condition on the variables. So let's take the last sort of 10 minutes and look at some published examples that actually did not use DAGs anywhere, and see if we had used DAGs, would we perhaps have come to some different conclusions or avoided some spurious conclusions. So let's, one of the things that we see quite often now is this something called indexed event or collider stratification bias. And here I've got a number of papers from both from rheumatology and cardiology, where we have in the general population some known risk factors, right? In the case of rheumatic disease, you know, if you're obese, if you're a smoker, we know that your incidence of all these rheumatic diseases goes up. But interestingly, if you look then at people who have rheumatic diseases, what's the effect of these risk factors in terms of the progression of their rheumatic disease? And it's all negative. It all goes down. Kind of strange that these risk factors are important for the development of the disease, but then they suddenly become protective for the progression of the disease. And we see the same thing in cardiology. I mean, it's actually very sad. The number of times that you hear about an obesity paradox, right? We know that obesity increases the incidence of cardiac disease, but in people who have had a heart attack or whatever, you'll get everybody publishing saying that obesity is actually protective. But similarly for smoking and a whole array of other cardiac diseases. So, I mean, it's very hard to understand. I mean, we know these risk factors exist for the general population. Why are they reversed in these selected or index event populations, right? And here's an example. Some sort of systematic review finds little to no evidence that obesity influences the progression of osteoarthritis, right? And these things get published all the time because, one, editors like the word paradox, and it's seen as something that's novel, controversial. You can always invent some sort of hypothetical explanation. But I think the real question is whether this is anything causal, or is there a non-biological explanation for all these sort of risk factor paradoxes? And indeed there is. If you look at obesity, you know, I think it's quite clear. Our knowledge is such that it affects the incidence of osteoarthritis, and it more than likely affects the progression as well. But one can imagine that if you now are looking only at those people who have osteoarthritis, we're putting our little box, right? We're conditioning on here. And we have some unmeasured risk factors that also lead to osteoarthritis, right? So we've got the old common effects, right? Okay, common causes rather, leading in there. So if we put our box around it, the same way as we put the box around the bell, we're creating this negative association and we're opening up a backdoor pathway, right? And this is, you know, collider stratification bias, index event bias. And so this is this spurious association among the risk factors, among the population of people who have had an index event. And I would put forward to you that anytime you see paradox in and looking at index events, that really what you're seeing is collider stratification bias, and anything else is just, you know, ridiculous. And this is the most egregious example I've ever seen about this. This is in GEM. It says among patients with incident acute myocardial infarction, in-hospital mortality was inversely related to the number of coronary heart disease risk factors. So in other words, if you look at this diagram, as you have fewer and fewer risk factors, your mortality gets higher and higher and higher, right? So, I mean, what's the take-home message from here? Should we tell our patients following an MI that they will do better if they increase their smoking, increase their weight, increase their cholesterol, increase their blood pressure, and increase their diabetes, right? I mean, this is what they're essentially trying to tell you in that paper. Of course, this is all nonsense. It's nothing more than collider stratification bias. And if you actually draw a DAG, maybe you can appreciate that. So now I don't want to just put the onus on others. This is a paper I was involved in, about a decade ago for a couple of former postdocs, and they were looking at fluoroquins, and they'd gone on to work in ophthalmology departments or whatever, and so they were looking at whether the use of fluoroquins was associated with the risk of developing a retinal attachment. And we had this large data set of 1 million people, and we got all the cases, and we adjusted for age, sex, cataracts, myopia, diabetes, a whole bunch of stuff, and we got a positive finding, statistically positive, although I did, my only contribution to the paper was making sure that they added that the absolute risk was small. That was my major contribution to this. But anyway, we did all the analysis according to the best of our knowledge at that time. And a few years later, about 5-6 years later, I was asked to review a paper for ophthalmology. And the authors presented the DAG in figure A, and they used that to praise why our paper was good, because we controlled for all these confounders and some of the other people hadn't, and therefore we were really the good guys in this. And so, I actually read their text really very carefully, and it actually turns out that what was in the text was quite a bit more complicated than the DAG that they presented. They just presented this little diagram. They didn't use the word DAG. And what they actually were saying was that low SES, yes, it influences the use of fluoroquins, but that it also can lead to myopia, and that some unknown genetic axial elongation and other things that I know nothing about also influence myopia and also influences retinal detachment. So if you look at this is the so-called M diagram. If you do as we did and you control, right, condition on myopia, what happens? We've got a couple of arrows going in there. Wow, we've just created a backdoor pathway going through from fluoroquins to low SES to these unknown risk factors down to retinal detachment. So if the causal pathway, causal model B is right, then myopia is not a confounder, but it's a collider. And stratifying on it, as these authors recommended, and as we did, is actually going to increase and not decrease the bias, right? So, we got this JAMA publication, but actually maybe we got it wrong. Now, I can't really answer that because I don't have the substantive, chops to be able to say what is the right DAG here. But all I'm saying is that, had I the knowledge I have about DAGs today, I would have been much more demanding about the what exactly is the our underlying causal model that we're trying to explore with this data. So now you can do even, can have much more complex DAGs than what we've talked about. Here's some code that will produce that DAG for you, so that you don't even have to do it yourself. When you have a DAG that's complicated like that, and you might ask you, how many pathways are there that go from X to Y, or Y1 in this case, it's called Y1. And you can count them, and I think you can probably get there, and you can probably figure out how many of them are open and how many are closed, and can you figure out what's the minimal set of variables to block? Yes, you can do all this by hand, but if you work in R, you can, with one line of code, you can determine that there are 43 pathways from X to Y1. All are backdoor except for one. Of the 25 backdoor, of the 43 backdoor pathways, 25 are open, and it can tell you the minimum set of the variables that you should be adjusting for to determine the causal association between X and Y1. So, you know, the bottom line, my bottom line is I think the DAGs can be super useful on the road to causal inference. And I encourage you to try and have a look at them in the research that you do. I think it might avoid looking back at a paper you did 10 years ago and wondering if what you published is completely wrong or not. So there are lots of excellent references for this. Basically, anything where you see the name of Judea Pearl or McGill Hernan, these are the sort of gurus of DAGs and causal inference. Some of the material, some of the coding is in an online, ebook that I'm sort of putting together, so you can find some of the code there. And I think that's it. That's number 40 of 40. So we're done.
Thank you very much, Jay. That's an excellent presentation. I learned a lot, and I have a number of questions I've noted down. But I'm going to first turn to our audience. Would any of you like to ask questions of Jay? You can either speak up or, I mean, maybe if you raise your hand, I think I'll be able to call out your name. You can also type into the chat.
Oh, stop the share.
Okay.
I can at least see.
Okay, yeah, Teresa has a question. Teresa, please.
Hi, Jay.
Hey, Teresa.
I thank you so much for the talk. It's great to see that you've learned all this stuff, and and that's great. You talk about confounders and colliders, and did you ever use the word mediator?
You know, so
that's my question. How do mediators fit in here? Thank you.
Yeah. So that's a great question. So you know, I didn't use the term mediator. Obviously, in that very first example, where we had the post-treatment blood pressure, that is a mediator on the road between the drug and the income and the outcome. DAGs are very. I don't think they have quite the same utility when you're trying to sort out mediators. Now, having said that, Tyler Vandelay, whatever his name is, has written some papers about using them in that context of mediators. I have to confess that I found it hard going, and I haven't really been able to quite sort that out as to where and what is the utility of DAGs with mediators. I think that's probably would be sort of the view of the methodologist and not the view of the clinical scientist looking at DAGs. I can't really provide you with a good answer other than to say that there are some limitations, I think, to DAGs when it comes to dealing with these mediating variables. But you know, I will say even there, if you can see a confounder between the mediator and the outcome, you right away you know that you've got some serious concerns, and that you really have to be able to control for that, because otherwise you're going to open a back door once you start playing around. But I can't really say more than that. I haven't really looked at it in depth. Sorry.
Thank you. I do think looking at DAGs is an interesting exercise, and I think anybody investigating causal association should have a lot of fun proposing DAGs. As we learn more about confounders and colliders and mediators, I think these DAGs are going to get more and more complicated, I think. So I'll look forward to your next seminar, Jay. Thanks.
I'll have to learn a little bit more before I do that.
Thank you, Teresa. Jay. Dr. Kramer, Michael Kramer has the next question.
Yeah, thanks, Jay. I find DAGs are useful for just thinking about temporal relationships among exposure, outcome, mediators, and so forth. But when you and I and Teresa were in training, this is in the pre-DAG days. I'm not telling anything out of class or out of line here, but I think that's fair to say that was in the pre-DAG days. But we did learn that, I mean, that association is not causation. I mean, people have been quoting that for decades, if not a century or more. And one of the things that I learned, at least, is that if the study had been a randomized trial, thou shalt never control for, stratify by, et cetera, any effect of exposure, because you will get the wrong answer by controlling for anything that is an effect of exposure. So you will never get away with either in a regression model or a stratification subgroup model for a randomized trial of stratifying for or controlling for any variable that could be an effect of the let's say a randomized treatment. If you use that kind of guideline, what do DAGs add to that? Because both colliders and mediators and confounders are effects of exposure. So if you abide by the rule of not controlling or stratifying or blocking by an effect of exposure, why isn't that good enough? What do DAGs add to that?
Right. Well, I think that's obviously a good rule of thumb, but there are variables that I think exist that are not just the outcomes of the exposure, but actually lead into exposure. For example, one could think of, if you're doing observational studies, obviously, but you're looking at drug use and some outcome. Well, clearly your socioeconomic status can have an arrow pointing into whether you're going to pay for the drug or take the drug or not, right? And it can also have an effect on your outcome. But that, so I think that's an important variable to control for, but it's not a variable that flows out of, it doesn't depend on you getting the drug or not. That doesn't determine the causality of where your SES is. So I think that there are variables on the other side of exposure that don't just sort of flow from your exposure, which are important to control for.
And that's a classic confounder, but you would never, if the exposure had been randomized, you would never, and it was a sufficient sample size, you'd never get unequal distribution of SES in the exposure groups.
Right. No. So I think that that the value of the DAG is to make sure that you are actually doing all the things that you think you are doing, right? That you think that you are controlling for the confounders. And then, of course, you can have a confounder that comes in SES, and then you have another confounder that is, I don't know, where those two can be independent, or you could end up with something like that M diagram where I showed you, where everything looks fine, but without stopping to think and to crystallize what's going on, we interpret one of the colliders as a confounder, as we did where we said that myopia was a confounder. But if you have if you've really thought and you've gotten all the information about what the true causal model is likely to be, you will appreciate that what you thought was a confounder is really a collider. I'm not sure that DAGs, are absolutely essential. If somebody is incredibly meticulous and careful in their thought process, but I think, for me at least, having the visualization of all these variables and the way I think that they interact, I think is helpful in making sure that I'm interpreting my coefficients and my models correctly. And similarly, I can use the data to assess, is my causal model as I think it is. But if I have a model where these two variables should be independent and I start analyzing that and I see there's a dependency, I've got to reassess my model. I didn't convince you, Mike.
Yeah, we can talk about it. We can talk about it.
Thank you. I mean, to me, it sounds again like the mediator question. You know, if an exposure causes something and that in turn causes the outcome of interest, is that a mediator? Is it again falling into the category of questions that Teresa raised, perhaps? I have a question, since I don't see any other questions immediately. I'd like to ask a question. So Jay, in your example of BP versus age,
Yes.
where you simulated data where BP was related to age but not related to group, how would your analysis have been different if you had used a DAG? I mean, did you perhaps it showed us that and I missed it?
Yeah, I think that I'd have to stop. The point of that exercise was just to show that just dumping it into an automated regression model is what on the surface looks like, hey, I'm doing it legitimately. I'm giving all the data in and it's telling me what the model is. I'd have to sort of sit there with my pen for a second and see. We have BP, and we have age, and we have group. Yeah, no, I mean, I guess you would model that on the DAG is supposed to represent your belief about the how the data is generated, and how would I'd have to stop and think about where I would put the right arrow.
I mean, is it the case that simply that the DAG serves to illuminate that this group should just never enter your regression model? Your regression model should simply be of BP versus age. And,
yeah, I mean, if that if your DAG is that you have set up is such that you believe your causal model is determined uniquely by age, then you should not have the drug group going in. The drug group is was associated with age, so you would probably have an arrow where age is also going down, going down to the drug group. And so you'd appreciate that really what you have there is
group is a mediator in that case, and it's an effect of age because the older people and the younger people are being treated with
they have different
different treatments.
Yeah.
And if it was a randomized trial, that couldn't happen.
Okay.
Yeah. And
so once you distinguish
age is, yes, you're right, Mike. The age is in the middle.
Okay. And so that okay.
And again, so you would not want to be controlling on that. So the drug seems to be determining
Okay.
Think about which way that arrow goes, because again, I'm does the drug determine the age, or does the age determine the use of the drug? Again, you'd have to sort of plan that out from the beginning. As I say, the goal of that example is just to show that taking all the data without thinking about what the underlying model is, it will get you into trouble. In this case, the model was simply that the BP was determined by age and age alone.
Okay. Thanks, Ray. It's 5 o'clock. I just want to thank you officially, but would you stay to take a couple more questions?
Sure.
Okay. So thank you all for attending again. And I'm going to, Jay's agreed to stay on, so I'm going to ask a couple more questions. Here's a question from Guang Zhang. Guang, do you want to speak up yourself, or I can read out your question? Jay, do you see the question in the chat?
Just a second, I'm in the chat. Yeah, I think there's a lot of hype around machine learning and AI, and yeah, I think it can bring some things to the table, but I think some of the AI that we get so excited about, random forests or whatever, it's like logistic, regression. So I think that there's still a place for good statistics and in the AI and machine learning world. I don't think really it matters whether you use Python or you use R. In the AI, they've got TensorFlow and all sorts of, packages that for AI, which before were just in Python, that you can now use in R. So I think it's whatever you're comfortable with, and if you really want to work in Python now with R, you can run Python within R, within RStudio, and there's all sorts of packages that help you sort of flip between Python and R. So
Thank you. Jay, I have one more question, and that is, two more questions actually. One is a technical question. There in your last example, you showed that there were two of these adjustment sets. What does that mean?
The last example, I'm sorry, Nandini.
The one where you showed us your Dagify or Dagity or whatever example. Yeah. I thought it finished off, it seemed at the end of that example to refer to two adjustment sets.
Oh, yeah. Okay. So there are two ways that you could block all the sort of spurious pathways. Okay. And one would have involved, I think both of them had 4 sets of variables, but there are 2 different ways that you could block the pathways, Okay. Okay. So you maybe in one case, you could imagine a model where one of these variables was actually, you had it in the model as a variable, but you hadn't measured it. Okay, you didn't have access to it. So maybe you would then sort of say, okay, if I'm going to try and control, I'm going to use the other group. So because sometimes you can block a pathway by one of several ways. So there's just one, not just one set of variables that can lead to a causal.
All right. So it's rather like having collinear predictors or something and having to make a choice.
Yeah. Well, then it's not so much that they're collinear. It's just that there's a couple of different ways that you can block all the pathways.
Okay. And then my last question is: so after now becoming familiar with DAGs, would you say that before you fit any regression model, it's worthwhile first plotting a DAG?
Yeah, I think so. Okay. I mean, if you're lucky and you're like, Mike, and it's all your thinking is all very clear and you know exactly, what's going on. Maybe you don't have to, but I think that putting the DAG down on paper will help clarify what your causal assumptions are. Mm-hmm. And then once you've made those assumptions, then it helps you, it tells you how you should be interpreting your statistical associations that you see. But I don't think you can interpret those statistical associations unless you have, a causal framework that you've proposed. And clearly, I think you should propose the causal framework before you start looking at your data and then, jigging it backwards. I don't think that's the way you should go. So yeah, no, I think that there's a definite value in laying out your DAG before you do any of your analysis. I think it really does help you interpret what's going on.
Okay. No, I certainly, that makes sense to me. That makes sense to me that you must do it that way, from a completely unrelated experience with latent class models. But you can like you even the example that you presented, you can come up with 2 competing models. You may not be able to tell them apart using statistical whatever AIC, BIC criteria or something, but One of them may make more sense because it matches your understanding of the problem. It reflects the real causal model, and one of them has just got all the variables that you've gathered in it. And
yeah, no, I think that's exactly what it is. And I come back to the fact that you really, in order to interpret your data, you have to put it in the right context. And that means, if you're trying to, look for causality, and I think that's what we're after. I don't think we care about an association. I think we want to know if there's something caused something or not. If I'm likely, if I'm going to intervene, am I going to make a difference or not? And to do that, you need, some prior knowledge, and that you can put down in your model, and then you can test if the model holds up. And I think when I start thinking of this, I think it's pretty easy or easier to convince Bayesians of the need to have a DAG than it is perhaps to convince frequentists, because the Bayesians are already open to the idea that you need some prior information if you're going to properly interpret the likelihood of the data you have from your experiment. So if you're already predisposed in that direction, I think you're more likely to be accepting of DAGs.
Thank you very much, Jay. I found that very helpful, and I'll definitely be looking at your slides in great detail now.
All right. Thanks so
Okay.
much. Bye-bye.
Thank you all for attending.